Okay, I've got I've kind of cobbled this circuit out of Molvino's textbook. It's basically a a dual feedback amplifier, and it's adjustable, for a gain of, like 10 to 110. So, or maybe 11 or something like that to 110. Anyway, the point is that um, that I thought I'd cobble this together, and because I've been curious about these. Of course, he didn't really explain a whole lot about how this works, so this is like at the end of the chapter and shit. So you know, um, but still, I thought I'd breadboard the thing together, and it looks like a mess. I hate breadboarding. I swear. Um, we get all this extra inductance and capacitance and shit like that in there. It's how good you can be, and plus it's just a big mess. But anyway, I decided, because the analog discovery is generating such an awful amount of noise. You know, that's what basically see there, and I still think its probes are probably injecting some noise into this circuit as it is coming just through the wiring and everything. But I decided to hook my other function generator up, to at least get a clean input signal, because I couldn't even get that out of it. Um, right now, if you can make it out, I've got this thing. Man, I wish this camera worked with glowy shit better. Shit. There we go. Okay, so yeah, we're at 3.8 megahertz is what we are, and I've got the signal level set at 60 millivolts. You can't see it because the cursor's on it, but it's 60 millivolts. It translates, in the analog discovery to, like 70 millivolts or so. So yeah, that's probably its peak to peak roughly. But it's got so much noise on it. It's remarkable. It's giving me any data, but you can see, that the gain here I'm getting at this is like, at this level about 5 times or so. Because I had to tune the signal way down to get it to work at this high frequency with reasonably low distortion. Again, you see all that short noise chatter on it. It's around 1 megahertz of some kind of sporadic 1 megahertz or so noise signal that I get on everything around here for some reason. Again, I think it's mostly coming from the analog discovery's wiring, but what it's picking it up from, I'm still not sure. I got this thing set at 15 volts, drawing 6 milliamps. It was only designed for 10 volts, but this guy made the damn bias so low on this stupid thing. It's like 4 volts, DC bias on both of these, really, if you run it at 10 volts. So I, thought, what the hell? I'll try to run it at a higher voltage and see if that improves things. And it kind of did, but kind of didn't. So it's just not designed well. And this guy, has a penchant for, what he calls, stiff biasing as opposed to, firm biasing, right? Well, Hazen, used firm biasing, 10 times, so so your base current, you want your voltage divider to be, to provide at least 10 times that amount of current going through it, whatever you calculate your base current to be, right? So, but this guy wants it to be 100 times, which, okay, is nice and dandy. Yeah, it does give you a stiffer bias, but the consequence is, since you're making, that, 10 times higher, that means your input impedance is 1/10. So he's basically giving you gain stability at the sacrifice of signals, and like I said, this thing works out to maybe 700-ish ohms, as an input. And again, in voltage amplifiers, generally the rule is, the higher the input impedance, the better. I mean, each of these would be about 10 times higher, in a Hazen version of it. So, generally speaking, on the input bias. And so anyway, and one of Hazen's rules too is that as a rule of thumb, you use 10% of your collector resistor as your DC bias resistor. So this should be like 360 ohms instead of 1K. But at any rate, this guy's got different design philosophies, so I'm not sure, what the merits of one are or the other, except that I know you're often better off, because I could see compromising instead of going 10 times, make it 20 times, so make the current going through this voltage divider, 20 times what your expected base current is. That'll make it stiffer, but it's getting pretty good results at a Hazen at 10 times, and you get a 10 times higher input impedance as a result. Although it depends on what kind of resistance you have over here. These transistors, I'm using 3904, so when they tested them, they have a gain of at least 200, a beta of at least 200. So anyway, this would have to be just completely like redesigned, if I were gonna put this in like on a solderless breadboard or something, which I hadn't decided yet. But yeah, so this is quite a mess. As you can see, buried in there, the other transistors. And I did put a 10K resistor in there so I can get it up to a gain of 100, but I'm struggling with a gain of 10 or 11, just trying to generate a signal. I mean, it's even at lower frequencies, still, you got to generate a pretty low frequency, otherwise it starts shark finning on you because of the fact that, he's got his bias point set so goddamn low. So, and let me show you that. I'll switch off this. Oops, yeah. I switched off the channel, so we just have that annoying noise on it. But let's see if you got what the focus is on this. Okay, that's probably a little better. So let me probe a couple of easy to access points on this thing. Right here, that's the emitter. The base is in the center, and the collector is on the side. The same way on the other transistor, which you can't really see. This, let's see. Okay, let me. Yeah, try to do this without short circuiting everything. Hard for me to see. Hold on. Got my magnifying glass. Okay, so I'm gonna probe, and I guess let's see. Well, I guess I can probe the emitter. Okay, and right now it was only at 1 volt originally. Now it's at 2 volts because the voltage divider, that I talked about, the voltage divider here, now has 15 volts across it, so it's got more current going through it, so it's pumping more current into the transistor. So as a result, its current has gone up, although I still have yet to explain apparent discrepancies in this, and I'll discuss that in a second. But since that's a 1K resistor, right there, that 2 volt reading suggests a 2 milliamp current, right, flowing through out of the emitter. And again, there's going to be some current injected from the base, but it shouldn't be very high. But then again, this is a low impedance, so I don't know, without hooking an ammeter on it, I can't be totally sure. But anyway, the voltage drop across this resistor being roughly 2 volts implies roughly 1 to 2 milliamps. Okay, so let me try to get probes across the let me see. Yeah, this should be our output right here. Alright, so it's 4.3 volts. That's his damn bias point. And again, it's like 4.0 or 4.1 volts if I put it, set the power supply to 10 volts instead of 15 like I have it. And if we go over to the other transistor, um, this will be the output here because this is the feed through capacitor, the stage to stage coupling capacitor. Um, so that's about 4.9 volts, which is an improvement. But again, ideally you'd want to see this around 7 volts. But I don't know, since he didn't explain the theory very well, I don't know how much of this has to do with the fact that he's using feedback from the second transistor back to the first. Maybe some of what he's doing is because of that. I don't know, because he doesn't have any kind of detailed calculation on this. What you see is what you get. He calculates the fucking gain. That's all he really explains about this, which is, disappointing, but shit, I guess it works to some extent. Um, so again, this is better biased over here, even though the stages are pretty much identical. But the difference between this stage is that it's loaded by this stage, whereas this one, is loaded by this resistor here. But at any rate, you saw the 4.3 volts we have across that, right? So, um, so what you gotta, we're talking DC bias, so, um, but since this is 4.3 volts and we got 15 volts that we're applying to it, basically that's 15 minus 4.3, right? Okay, so we got 10.7 volts across that resistor. So let's divide that by 3600 and see if this adds up. It's saying about 3 milliamps. So I don't really get it. Okay, so we have 3 milliamps flowing through that resistor, and again, this is DC bias. We have 3 milliamps flowing through here, dropping, that 10.4 volts or whatever, but we only have 2 millivolts or through 2 milliamps or less than 2 milliamps flowing through this emitter resistor. I mean, is this capacitor really leaky or what the fuck ever? I mean, I don't get it. Even if it were really leaky, where's that extra current going? Is it going through here for some reason? Is this capacitor leaking? I doubt that it's going through this because that's a 10K load resistor. That's not going to, eat up, make an extra milliamps worth of difference, I would think. Not in series with this, because that would be about 1 milliamp total going through this. I don't know, maybe that's a bad capacitor. I don't know. Anyway, it's just strange. It's not what I'd expect. I wouldn't expect, that bias point to be that low. I guess I could start unplugging things and see if the voltage increases, but shit, I'd never get things back together. Again, I hate breadboarding. I especially hate this particular breadboard. Yeah, I bend half the goddamn leads I try to stick into it, even when I'm using needle nose pliers. So this is kind of a piece of shit. I don't even know where I got it from. I think it came as a free something or other with something I bought one time. Arduino part set or some shit. But at any rate, what's interesting though is that still, let me turn the function generator back on. But we're getting still a usable signal again with about a 5 or 6x gain out of it, and it's well, right now it's only showing about 400 millivolts peak to peak or something like that, but this was a 70 millivolt signal. So, because I had to turn it way down to get what looks like a sine wave, if I turn it up, at this frequency, yeah, it starts kind of shark finning again. But let me turn the frequency down on this. Well, hell, I'll just have to read it off to you. I'm reducing the signal level instead. See, if I up the signal level, it still looks good right now, right? But it's starting to, form shark fins, and it does that, progressively as I turn the amplitude up. We're up to 200 millivolts input. And again, a 1011X amplifier should put out like 2 volts at this level of input. And I got the probe set to 10x, by the way, just to eliminate some of the frequency distortion. To eliminate that as a possibility, because those are usually only good to 4 to 6 megahertz. So as you start to approach that, it'll start doing funny things. But if I tune it down, about there, that's a good looking sine wave. It's about 90 millivolts, I suppose. So, and we're getting a gain of, about 7 times, 6 or 7 times at that level. So, um, so, at 3.8 megahertz on a goddamn breadboard, I'm pretty impressed. And the peak to peak output is about 7 volt or 700 millivolts. So, and that's with like about 100 millivolts input. So, what you'd expect. So let's go. I mean, I could turn the frequency up, but it's just going to get more and more diminished. Yeah, it's 4 megahertz, 5 megahertz. And it still roughly looks like a signal, but it's certainly attenuating. And still looks like a halfway credible sine wave. Of course, I bet you put it on a distortion analyzer or something, it would not look so great. But yeah, still looking pretty much like a sine wave over here. It's gain is about still 5. Um, according to the analog discovery, again, that input signal looks like total garbage. But again, coming from this setup, take what you can get to get differential probes out of it. Um, so anyway, that's at 5.6 megahertz. It's still producing usable gain. Even with signal levels pretty low, it's still impressive that it's producing usable gain. I mean, it's still acting like an amplifier. And again, it's low frequency gain is like 10 or 11, right? I even ran a frequency sweep on it earlier using the analog discovery sources. And you can kind of see there I ran it out to about 5 megahertz. The gain starts rolling off at about 1 megahertz. But it's pretty much an 11x gain across the board. This is the flattest amplifier I've tested, transistor amplifier I've tested out of all the ones I built, believe it or not. But boy, the signal looked like, oh, such trash. I've never seen such a trashy looking signal. But still, I mean, that's interesting. That's why I wanted to eliminate the analog discovery as a signal source, and this is a lot cleaner. So it's a lot better of a function generator. But at any rate, okay, so we're at 5.8 megahertz and still getting a signal gain. In fact, the scope says that it's 64 millivolts peak to peak, so that's 600 millivolts. Given the fact you got 10x probes on it, and I just hadn't adjusted my scope for that, because I'll probably switch back to 1x later. Okay, but at any rate, so it's 5.6 megahertz. This thing's producing usable gain, and a relatively low distortion sine wave. So that's interesting. Now I can switch it though over to a square wave real quick, and well, that's what it looks like. So it certainly does have some distortion, but it's certainly eating up those high harmonics, high frequency harmonics. But again, for this setup, I'm shocked that it's as good this, even on a sine wave. So let me switch this back. All right, back to a sine wave. Okay, let's go ahead and I guess I could take it up to 6 megahertz just to round off the number. And again, still we're gain of 4 to 5. So still 400 millivolts. In fact, the scope says about 150 millivolts or so peak to peak. Well, not 150, but 700 millivolts peak to peak. So it's not bad, not too bad at all. So that's shocking. But now let's look at the lower frequencies now. Start turning this SOB down, 2 megahertz, 1 megahertz. Okay, and I could probably switch back to 1x probes. If I don't destroy this stupid circuit. Well, no. Well, maybe it is at 1x. No, that's the analog discovery. Okay. I don't know what happened to my probe. I guess it's this one. Yeah. Okay. Switch that back. Now it's a much bigger signal, but we're low enough frequencies where that shouldn't be a problem, so I'm getting an accurate voltage reading. So it's like still at 700 millivolts, about 1.2 megahertz. So let me go ahead and see if I can up the, well, let's go ahead and lower the frequency more. Before I do anything, I want to see if that level changes. It's still about 700 or 800 millivolts, even at, I guess we're at 1 megahertz, no, 100 kilohertz. So we're at 100 kilohertz now, and it's still at 800 millivolts. Oops, I just went to 0. Change my setting here. Alright, 180, 40, 10 kilohertz. Alright, so it's still only about 900 millivolts, so we haven't gained much, so that tells me that since it was only attenuated down to about 700 millivolts peak to peak, at 6 gigahertz, and here we're at 900 millivolts, at 10 kilohertz. It didn't really attenuate that much, shockingly enough. Now, of course, our gain, well, shit, it's saying 1x over here. It's probably because it's confused. I got it at the wrong setting now. 100 watt. Oh, milliseconds. Come on. Because, the analog discovery's got those fucked up filters, so, it starts filtering high frequencies out. So, anyway, if it's not set right. And low frequencies, too, evidently. So, yeah, our gain is, about 6.5 right now. A large part of that, is due to our input signal being relatively low. It's, 70 millivolts-ish. Analog discovery saying it's, about 80 millivolts peak to peak on our input, and about 121 millivolts. No, I'm sorry. 121 millivolts on our input, and then about, 800 millivolts on our output. So, at this point, we can certainly turn this up, but boy, that's pretty broad spectrum, especially for breadboarding, a crappy circuit that's actually not designed well for what I'm doing with it. But let me go and adjust the amplitude of this sucker now, and get it to increase. There's a lot of jitter on this. See if I can get rid of some of it's because of that stupid noise signal on it. But 120 millivolts, 140 millivolts, like about 150 or 60 was about the most broad range I can get at a higher output swing. Let me adjust that down. So, I got it at 500 millivolts per division. It's giving us a 1.7 volt peak to peak swing. But the highest swing this thing will produce, given its 4 volt bias point on the output stage, is about 3 volts. And so let me continue to increase this. 2.4 volts, still looks like a sine wave. 3.2 volts, now it's starting to clip, above that. So let me back it off. So about to right there is about a 3 volt output. It's about 260 millivolts, or 280 millivolts input. So we're getting a gain at that level of about 8 or 9. So again, interesting. Now let's try throwing a square wave at it. Okay, now we're getting a nice clean square wave out of that, again at 10 kilohertz, so, you know, not too bad looking. Of course, since it's a dual amplifier, the input's in phase with the output, so, um, let me adjust this. Okay, so that's our input versus our output signal, but yeah, they're in phase. So let's see how long we get a good square wave out of this. Still looking good. We're at 50 kilohertz. Start to see a little distortion. And again, you're going to get that because there is some distortion, especially at the signal level I'm driving it at, because I'm still driving at the same signal level. So we're still getting a 3-ish, 3 plus volt peak to peak out of it. But we are starting to see some rounding on the leading edge there. Go up to 200 kilohertz, 300 kilohertz. But again, our signal amplitude is still there. Now it's starting to diminish. So right at about 400 kilohertz, it's starting, to show signs of attenuation. But now we're at 650 kilohertz, and yeah, it's starting to look not so much like a square wave anymore. When you agree? And I don't think the probe setting will, yeah, that's not helping that at all. So let's see what's going on over here in analog discovery. It's way out of range. Shit. That's too far. Still too far. Yeah. So there's a square wave input, which still looks roughly square wave-ish, despite all the noise in the system. But we got shark fins now. So let's and again, we're at 700 kilohertz right now. So damn this camera. So let me start diminishing our amplitude and see what happens. Okay, it's starting to look more like a square wave. It's shrinking at both ends. We're seeing some ringing there, which I'm shocked it's not ringing like a bell given all the damn inductance I have in this thing. But yeah, it's still a square wave, square wave-ish, even at 170 millivolts input, and we're still getting a 2 volt output. So, it's kind of a ringy square wave, but let's go back and increase the frequency some more. See how long this lasts. 100, starting to certainly do the same thing again. So, it's definitely, starting to show a lot of curvature there. 1.3 megahertz, 1.4 megahertz. Let me go and reduce the amplitude some more. And now we're more of a square wave again, and now our output is about 800 millivolts, which, if you remember, was about the level, that sine waves look good at too, at the really high frequencies. But we're at 1.4 megahertz, so I mean, as long as you keep it to 1.4 megahertz, you probably got a usable amplifier out here to. Oh, damn it! Okay, the frequency. Next time I hit the wrong button. All right. Okay, about down to 60 kilohertz now. So yeah, nice looking square wave, 180 kilohertz, 200 kilohertz, 400 kilohertz, 500 kilohertz, 600 kilohertz. Kind of wish these oscilloscopes would automatically adjust themselves. 1 megahertz. So I mean, it's impressive, despite it being a poor design, and I'm running it at extra high voltage, and on top of that, and the goddamn ants and you little fuckers. I need to get some more of those ant killers and bring them, because this is like a totally different ant hive over here. God damn little fuckers. Than the other one I'm working on over there. I need to feed these guys too, but they haven't been coming in. It's just as much that their stupid flying ants are bugging the shit out of me still. So at any rate, yeah, I just kind of wanted to document that I'm shocked that on this damn breadboard, that I'm getting this kind of good results out of an amplifier that's actually not theoretically well put together, well designed. Again, this bias points certainly need some work. I do kind of want to run a Falstad simulation on this, maybe, and we'll see how that might see how that goes out of curiosity. See if I get some better adjustments out of it. But I'm still shocked this thing works this well to frequencies like that. We're 1.1 megahertz right now, so it's pretty pretty interesting. So anyway, cheers.